wait a few minutes for people to come in. All right, let's go ahead and get started. So for our first talk in this session, we're going to have Brendan speak with us. He's a co-founder of MakePath, and he's also helping out with the bokeh sprint later on. So if any of you are interested in working on bokeh, reach out to Brendan and he can help point you in the right direction. Okay, Brendan, you want to take it away?
Yeah, thanks, John. I'm going to share my screen now. And John, are you able to see my slides here? I'll assume that folks are seeing my screen. So this is the Scaling Up Python for Geo with Distributed Computing session. My name is Brendan Collins. I'm the co-founder and principal at MakePath. We're a spatial data science firm based in Austin, Texas. And if you want to learn more about MakePath, you can come over to makepath.com. We're really happy to be here at SciPy and just very, very thankful to be part of the Python community. It's been really beneficial for us to be able to contribute to building geo tools on top of great projects like NumPy and Dask and Xarray and Numba. We've taken these tools and applied them on different customer projects, and we're going to look at some of these tools that we're excited about. Also, I wanted to make a shout out to bokeh. We are leading the bokeh sprint on Saturday. So as John said, for folks that are interested in contributing to bokeh, the visualization library, come on Saturday to learn more. Just a bit more about MakePath. You can come over to the MakePath blog at makepath.com/blog, and you can see some of the projects that we're working on and some other resources that we've developed for the community here, like this history of open source GIS infographic. And we are also hiring. So if you're looking for a job or you know someone that is, go over to makepath.com/careers. So a bit more about this talk. I'm specifically talking about scaling topics in the context of geo. And these scaling topics are broken down into the following areas. So in using Dask for horizontal scaling, we're going to see a little bit how you can take your analysis and move it from one computer to multi-core and multi-thread to multi-machine in horizontal scaling with Dask, and also making your algorithms faster with Numba. We're going to see some examples of that in the geo context. Also significant to scaling is data access. And we're going to talk a little bit about STAC, which is an exciting project that we're using a lot for being able to discover spatial assets and access them via Xarray and Dask. And then looking deeper into Xarray-spatial with spatial algorithms. And that's a library that we've developed at MakePath and continue to develop and want to get the word out about. And so a little bit about starting with the geo side of things. We are focusing on raster analysis here. Xarray-spatial is raster focused and uses Xarray as its data structure backend. Xarray-spatial does not introduce any new data structures. It uses Xarray data arrays for representing rasters. And to briefly cover, we think of vector data in the geo world. And I know that the term vector is used in many disciplines, but within the geo world, we refer to vector data as those data that represent discrete phenomena like points, lines, and polygons. In this case, we're talking about rasters and images. and doing image processing. So those are in the geo world are used to represent continuous phenomena, things like elevation or rainfall or soil acidity. Those are all phenomena that are adequately represented using rasters that are regular grids with an origin and a resolution. Some of the tools that are available inside of Xarray-spatial include surface analysis tools like slope and curvature, illumination using hill shading, and view shed analysis. Those are all inside of Xarray-spatial, along with proximity tools for computing distance grids, where we're computing a raster where the cell values are the distance to a nearest target pixel. Also directional grids and allocation grids, where we're storing the ID of the nearest target feature. So the proximity tools are something to look at. Also zonal analysis tools, where we're doing summary statistics on top of irregular areas that are defined by grids. Focal tools, where we're computing stats based on the area around a pixel. We also have some higher level focal tools like a hotspot analysis tool, which will compare the local statistics to global statistics to find statistically significant hotspots in your study area. Classification tools that allow you to classify a raster using classic 1D binning methods, things like equal area and natural breaks and quantile, and then being able to reclassify your rasters using specific bins that you define. Multispectral tools for things like NDVI and all the other flavors of band math that you can do on Landsat and Sentinel data. And also some pathfinding. So this is somewhat academic at this point and is not Daskified yet, but it's just another area inside of Xarray-spatial. And so talking about scaling, and our first kind of topic to dive into with scaling is with Dask. So Xarray-spatial integrates with Dask. And Dask is a very popular topic at this conference. I'm going to assume that many folks have heard of Dask and have used Dask, but for those who are not familiar with Dask, Dask is a framework for doing concurrent and parallel programming. It provides a few high-level data structures, which are very helpful for folks like me that are downstream of this project. In particular, we use the Dask array, which allows you to coordinate multiple NumPy arrays so that you can do larger than memory calculations on multiple cores and multiple machines. So we use Dask extensively, and we integrate directly with Dask, and are working towards Daskifying all of the tools within Xarray-spatial, although we start with simple NumPy implementations. And there are other Dask data structures besides the Dask array, but the Dask array is the primary data structure that we're going to be using here, and we're going to be taking a look at. So in getting going with doing distributed computing and using Dask and using Xarray-spatial, one of the easiest ways to start is to go over to coiled.io. So at Coiled, they help in doing managed Dask clusters on top of different clouds. We use Coiled a lot for deploying our Dask clusters, and that makes it extremely simple to get set up and going. So this is an example here. So what we're looking at, just to start diving into some code and looking at Xarray-spatial and looking at Dask, we're looking at a Jupyter notebook and also a Dask dashboard here. And when you're using Coiled and Xarray-spatial, what you first do is you import Coiled. That's just a normal Python package, and then you set up a software environment, and you specify a bunch of dependencies. It goes and installs all of the dependencies on each one of the workers, and then you're able to connect and create a cluster object based on your software environment. So this is a reusable environment, and then you can specify the number of workers you're going to use, and you can give it a name. I gave it SciPy in this case. That goes along with the conference. And so you can then connect to a cluster and establish a client. And so here, I'm just going to make sure that I'm using the right status screen here. And so what we're doing here is just showing how to load up some data. Xarray-spatial provides a couple of helper methods to get you going. So you don't necessarily need to have a large data set to play with Dask or play with these tools. We have a function inside of Xarray-spatial that's called make terrain, which will create a Perlin noise Dask array that will help you play with some of the surface analysis tools inside of Xarray-spatial. So when we think about scaling geo operations and taking the functions that I was discussing from Xarray-spatial and scaling them, we're doing that with Dask. So here I've set up a Dask array, and this is just Perlin noise so that we can have some sample data to play with. We can persist that array across the cluster, and then do things like hill shading and kick off operations on the Dask cluster. And I was running into a little issue here that was not resolved, so I'm just going to keep going through. But what you're able to do here is use the cluster and use the power of many machines, but be still programming sequentially. So you can take a tool from Xarray-spatial, provide it a Dask array, and then compute a given output. And we're going to see a little bit more of how we do that. Another tool to be thinking about is Data Shader. So Data Shader also works with Dask arrays and is a great tool for doing the color mapping. So here we can see an output of the terrain, the Perlin noise terrain that we generated. And we've run a hill shade on top of it in a distributed fashion to put a light source at a given altitude and azimuth. And we've stacked a color mapped terrain image with our illuminated terrain. And then we can take this terrain and do more things with it. So in this case, I'm now importing from Xarray-spatial the quantile method, which is one of the classification tools. And I can bin this terrain into 7 different bins. And that's what's happening here. So I've taken this illuminated terrain. I'm connected to a 32 machine Dask cluster on Coiled. And then I've classified it using the quantile method, which would have an equal number of values in each of the bins. And we can see the same terrain classified and shaded using Data Shader. So as we do things, you can see that we're using a lot of tools from different areas. Data Shader and Xarray-spatial would not have been possible without the help of folks from Anaconda and Quansight, and particularly Jim Bednar and Travis Oliphant and Jim Christ, and those guys have really helped to push the visualization tools forward. And then we've been building geo-specific tools on top of Data Shader and Xarray and Dask. So our geo tools, as we build something like quantile or hill shading, we need those algorithms to run fast because we have a lot of pixels to get through. And so Numba is what we're using to be able to speed up our algorithms, and that addresses the vertical scaling of our code so that our functions run quickly and can also run across a Dask cluster. So Numba functions can be serialized over a Dask cluster, and that's one of the things that's great about it. And if we dive into some of the code inside of Xarray-spatial, we can see the implementation of the slope algorithm. So all the tools inside of Xarray-spatial are named for geo professionals. So instead of naming slope something like gradient, if you look in NumPy, it might be called np.gradient. We name it slope because that's a name that's more familiar to the discipline. So here we have the CPU implementation of slope. We can loop through a NumPy array because Numba natively understands the NumPy array when we're passing it in, and then we can compute the horn slope, and we decorate this function with our Numba decorator, which is going to compile this code and make it faster. one of the great things about Numba is that we're also benefiting from the work that they're doing on GPUs. So here, as we scroll down in the code for slope, we can see the CUDA implementation of horn slope, which is contained in the same file, is very similar. And now we can target a CUDA GPU with the same code. So this is what, in terms of vertical scaling, we're using Numba to both make our algorithms faster and target modern hardware like GPUs to run the code faster. Then we take these fast algorithms and we run them across a Dask cluster, and we're able to scale up our geoprocessing from one machine to many machines. So this is also enabled by good data structures. So thinking about, we chose Xarray as the central data structure, and specifically the Xarray data array to represent our rasters. And Xarray is able to both be, Xarray, let me just define this as it says up here, gives us labels on top of our NumPy array. So instead of using integers to index into a NumPy array, we're able to use labels like slope and the names of dimensions to do indexing and do aggregations, as opposed to integers. And that's really nice as we go back to our code, even after lunch, and we have labels instead of indexes. Xarray provides a lot more, but it wraps up NumPy arrays, but it's also wrapping Dask arrays and CuPy arrays that we're going to use for our GPU implementations. So Xarray is a central data structure. In terms of scaling geo, being able to access data and discover data easily is also a concern. It's not just about being able to compute on multiple machines or speed up algorithms. STAC is the language that we're using to do this. So spatiotemporal asset catalogs. So these provide raster catalogs that allow us to query and bring back Xarray and Dask arrays from a partitioned data set living in the cloud. Another tool that we use a lot are COGs, or cloud optimized geotiffs, and they play nicely together with STAC catalogs. So we saw Coiled, and Coiled will really help you get going in setting up a cluster, and we use Coiled all the time to set up clusters. But another great tool that we're working on alongside of Microsoft is the Microsoft Planetary Computer. And the Microsoft Planetary Computer combines a rich set of satellite imagery, things like Landsat and Sentinel, and also the SRTM elevation data set, many others. You can find many other data sets on the Planetary Computer. So it combines these data sets with Jupyter Hub and gives you a Jupyter Lab environment with easy connections to data with open source tools. So the Planetary Computer from Microsoft is a really interesting advancement in the geo area. And you can come here to planetarycomputer.microsoft.com. You can see the development that's going on here and the new data sets they're releasing. So a little look at what it's like to do analysis and work on the Planetary Computer. So I'm logged in here as my user. You'll see that I have a Jupyter Lab session going on in the browser. And as when we log in, we're going to see that there's a bunch of different files, and there's also a tutorial section. So here in the tutorial section, you can access Jupyter notebooks that allow you to access data sets and act as good examples to implement your own analyses. So here we're using Xarray-spatial on the Planetary Computer, and we're connecting via STAC to query data on the Grand Canyon, specifically the SRTM elevation data that's stored as COGs, but delivered via a STAC raster catalog. So we're establishing a client, a PyStack client to the catalog, and then we're querying that catalog using a point location to bring back data. And when that data comes back, it's going to be an Xarray object backed by a Dask array. So this is where all these tools come together. So we have Dask and Numba and STAC and Xarray-spatial all together on the planetary computer, so that you can, along with the planetary computer data sets, so that you can be effective in your analysis. So here we're using Xarray-spatial to do additional classifications on this elevation data set. And we're exploring some of those methods like natural breaks, which you can think of as, for the machine learning folks, you can think of as 1D k-means, where we're classifying elevation for this area. So we're looking at some of these tools. There's other notebooks here which you can take a look at, which are interesting, things like generating cloudless mosaics using Xarray-spatial, also doing co-registration of different data sets. So if you're bringing in data from Landsat and Sentinel and you want to align all of the pixels, then the co-registration notebook can show you a little bit about how you can do that via STAC. You can do things like filtering based on date time in the STAC catalog, change projections, change resolutions. So STAC is really great, and then that ties in nicely with Dask and Numba and Xarray-spatial. Also, using focal tools for doing NDVI hotspots. We have an example there. And so this is all looking at the Microsoft Planetary Computer. So a little more about Xarray-spatial. So this is over at GitHub. I feed myself on GitHub stars. So if you'd like me to gain some weight, please go over to Xarray-spatial and give us a star. You can see all the features if you go down to our functionality table here. And we're targeting NumPy, Dask, CuPy, and also Dask GPU. So if we have a cluster of GPUs, this is the column that indicates whether the tool is currently supported for Dask or CuPy. So we can see our classification tools and our focal tools, multispectral tools, which includes a lot of this band math, pathfinding, which is only currently supported on NumPy. Proximity is coming. We're working hard on Dask, generating Dask proximity grids, and that should hopefully be released soon. Our surface analysis tools, zonal analysis tools, and then also local tools. And the local tools are looking at stats on at the single pixel level down multiple rasters for different time steps or different data sets for the same area. We have a user guide, so if you come to Xarray-spatial and go down a little bit, you'll see, or up a little bit where I was, you'll see that there's an Xarray-spatial CLI. So when you install Xarray-spatial using Conda or pip, you'll get some CLI commands where you can download example data and download example notebooks. So I've loaded up the example notebooks here, and I can see some of the surface analysis tools with doing viewshed operations, and also proximity grids. So here we're generating grids where we have a series of target pixels, and we're generating a grid which shows the direction to the nearest target pixel. So for machine learning folks out there, I'd encourage you to think about this as feature engineering when you're trying to add orthogonal dimensions to your model. What about spatial dimensions? What's the distance of something? What's the direction? These are some of the use cases for Xarray-spatial in the machine learning area. Then we can also see the zonal tools. So in doing zonal statistics, say we take a Perlin noise grid here. This is just Perlin noise, like our other example. And we want to do an imaginary hike across our imaginary terrain. It might be hard to resolve our hike path here, but using zonal tools, we can do summary statistics for each one of the legs of this hike. So what you do is you'd import the zonal stats tool, and the zonal stats will take a zone grid, which is going to be an integer grid to show what areas you want to do summary stats on a value raster. So in this case, it's our terrain. And the result that you get back is a pandas data frame that's indexed by the zone ID and then includes summary stats for that zone. So imagine that you have a rainfall grid and you have parcel data, and you want to summarize the amount of rain for each parcel. The parcels would be your zones, and the rainfall would be your value raster. You can also put in custom functions here. So if you provide a function as is mapped out with a dictionary, then you'll get the stats back for your custom function with those zone pixels injected into your function for each one of the zones. So that about wraps up as I'm getting through time here. I know this was from the fire hose with a lot of different tools. I covered horizontal scaling with Dask and mentioning Dask, vertical scaling with Numba, data structures and data access using Xarray and STAC, and then also just a general look at the tools available inside of Xarray-spatial. I love getting people reaching out either on GitHub or by email, and please reach out with any questions or comments, and go over to makepath.com/blog to learn more about what we're doing at MakePath.
Okay, thanks, Brendan. We have a few questions in the chat. I can go ahead and read them. I'll start with this first one. What of this tool set would be useful with shape data, something like GeoPandas?
Yeah, so there's always an interplay between raster and vector. Certainly the zonal tools are helpful. This does not specifically address rasterization. I would look at Data Shader for that. Excuse me. So Data Shader will provide you an easy way to move points, lines, and polygons into Xarray objects, Xarray data arrays. So by combining Data Shader with Xarray-spatial, you can bring in your vector data and convert it into a raster for additional raster analysis.
Okay. Next question is, what might be the size of a typical data set? Hundreds of megs, gigs, etc. And how much copying is involved in the computation? So yeah, do you need to move data around?
Yeah, so it certainly depends on the tool. For instance, the multispectral tools are very straightforward, just doing element-wise operations and scale very well. Other things like doing proximity and viewshed requires are more complex computations, so it really depends on the tool. These tools scale as large as Dask scales, so they're Dask scales to huge problems, and you'll see that in other presentations at SciPy. There's some limitations in terms of what the task scheduler can schedule based on how long each computation takes, but certainly into the terabytes.
Great. We have one more question here. Are there any tools that help with spatial temporal analysis for raster-based data?
Yeah, I mean, certainly all of these tools that we talked about would definitely help with that. STAC, the project itself, has spatial temporal asset catalog. That's what STAC stands for, in terms of organizing and discovering data and querying data. So I'd certainly look at STAC to be able to index your data and easily access it, and then using Xarray to build Xarray data sets that are composed of Xarray data arrays and doing analysis down them. All these tools, I think, apply to that area.
Great. Well, thank you for presenting on this, Brendan. That was a great talk. Our next presentation will be in about 5 minutes with Matt.
Thank you, guys. Thank you so much, John.